Um, Hello, everybody. Thank you for choosing my talk over the others. My name is Joanna, and I work at a startup based in Berlin and Toronto. We are a team of 18 engineers, and our main goal is, our main focus is video understanding, solving video understanding using deep learning techniques. And by video understanding, we mean here understanding and analyzing the content of video data. And today I'm going to tell you about our first project that we tackled, and this is a gesture recognition system. And so you might wonder, why did we choose gestures, or what is so special about gestures? And for us, this project was also kind of a proof of concept, because as you all know, deep learning has been booming in different fields, such as image classification, speech recognition, machine translation, and so on and so forth. But the video understanding field has not been yet so explored. And at the other hand, if you look at a video data sample, it is basically a very short clip. So, for example, something like this, that contains also a very distinctive movement within. So solving this kind of data set would prove us that you can use deep neural network to, the same way as solving image recognition, solve, for example, video classification. At the other hand, gesture is a natural form of expression. It is a form of human communication. And building a gesture recognition system would be a first step for computers to begin to understand human body language, thus building a bridge between human-computer interaction. And to give you a little idea of how this system would work, I'm going to show you a little clip. So this is a clip from the movie Minority Report, and you see Tom Cruise using his hands to move workspaces on his machine, or slide something down, go further in the video, zoom in, zoom out. So that's basically the gist of it. And I would like you to notice that he is not doing this with his bare hands, but he is using actually some gloves, making it easy for me to imply that he's using some additional sensors in order to recognize the gestures that he's making. And so, whoops, I'm just gonna go to the end of the video. How do I do that? All right. So obviously, gesture recognition, it's not a novel problem. Many companies tried or actually have built gesture recognition system, but they didn't really gain a wider acceptance among users. And this is also why. This is also because they often or always required some additional sensors. So, for example, you might see the wireless glove that has different sensors attached to the glove, which gives extra information. And based on this information, we make a classification. Or Microsoft Kinect has a depth camera. There were some systems that were segmenting the body, and based on the segmentation, they predicted the gesture. And so, on the contrary, we decided to try just feeding a neural network with huge amount of data and seeing if we can do it without any additional devices. And so this is important because it means that the end user, in the end, would only need a webcam or a laptop camera to be able to use a gesture recognition system. Yeah, and obviously for the deep learning, for any kind of deep learning algorithms, we need huge amounts of data. data in magnitudes of thousands or even hundreds of thousands. And the natural question is, how do we get this kind of data for this very specific problem that we've chose? So, for example, you could try data crawling, so scraping the videos from the internet, but this is obviously not ideal because, first of all, this is a very time-consuming problem. You might not find the right amount of data. You might find that the classes that you chose are not balanced because there are thousands of videos of thumbs up, but only few of some kind of gesture that you want your system to be able to recognize. You might find that the videos contain multiple people performing multiple gesture or the same gesture simultaneously or at different time steps. You might find that the people perform the gesture from different perspectives. You might find a video that is 3 minutes long and there's only 3 seconds of the gesture, which means that you would have to segment the video yourself. So this is obviously not ideal. At the other hand, you could try collecting and so recording and annotating the data within your team. But in practice, this is obviously not an option if we're talking about thousands of videos. So our solution for that was building a data platform that enables us to generate video data in-house. And the basic principle of the data platform is putting a task via services like Amazon Mechanical Turk, a task in this context we call crowd acting, which I'm going to talk in a second. And this is obviously the basic principle of the data platform, but there is way more effort required into building a platform that would provide us with some of the largest video data sets in the world. And to begin with, crowd acting is something very different from data labeling, which is a common practice when collecting large data sets. But we took it kind of a step further, where we say we want this specific label, and we put up a task with very specific instructions, and we ask the workers to record themselves doing this action. And in order to make this process robust, we've implemented some key features. So one of them would be on-the-fly validation, which may seem very straightforward, meaning basically that the worker gets an immediate feedback in case there was something technically wrong with the video. So for example, there was some problem with the video format. It was not a video, it was too big or too small. And this sounds very obvious, but it's actually crucial when keeping in mind that at the other side of the screen, there is actual human being that waits a reward for their labor. And also, this human factor is essential when we think that we rely on a community of workers to work with us in the long run. And so keeping that in mind, we've implemented a very clear and user-friendly interface where the user is guided through the entire process. He gets very specific instructions. He is shown an example video that he has to imitate himself, and he clicks through all the gestures that we ask. We also keep a very open communication with the workers. We provide them feedback whenever the video was approved or rejected. We give them a chance to redo the task in case there was some little criteria that didn't meet our requirements. And at the end of the pipeline, there is a team of crowd acting supporters that verify the videos and check if all the criteria that we ask for are met. In this way, we've collected the data set that we used to train our gesture recognition system. We call it the 20BN gesture. And this is a data set containing around 150,000 of videos with 27 different gestures. You can see the example of the gestures over there. It is also free for academic use, so you can just feel free to download it and try to build your own gesture recognition system. So that's basically how we got the data, very high quality and densely labeled data. All right, so now we specified our problem and we have the data. We can start training. But what happened is during our initial trainings, we've noticed a problem that we call the starving GPU problem. And basically what happens is, so for example, in image data sets or in image recognition cases, the image data sets is usually small enough to fit into the file system cache. So during the training, the initial epoch, the first epoch, would be a little bit slower because of the data reading, but in the next iterations, the data reading won't become your bottleneck. Whereas in the case of videos, because you have, for example, 150,000 of videos, they do not fit into the file system cache, and in each and every iteration, you have to reread or read the data over and over again, and that becomes the bottleneck of your training. The more so with multi-GPU training and with data parallelism, which is standard for, I think, almost all the frameworks. And so our solution was that was writing our own data format that we call the gulp.io. And it's basically a data format that concatenates all the frames of the video as into a single data file and saves the offset and the metadata into the secondary meta file. So the JPEG compression makes it more efficient, and easy to use API makes it easy to reason about. The speed that we get is from 9 to 16 times on HDD and around twice on SDD. It is an open source project, so if you have some similar problems, you can just use it. It does not extrapolate to, for example, speech or audio. It's only good for video and for image datasets. All right, so now we are ready to train. We made sure that the training works smoothly. We got the data, we specified the problem. And I will talk about our models. And I will be talking about 3D convolutional neural networks. If you know about two-dimensional convolutional neural networks, then it's basically analogical. But with the normal CNNs, you operate on images, which are three-dimensional tensors on batches of images. In the video cases, you have an extra dimension because you kind of have stack of images as your single data sample. And so the convolution filter is now three-dimensional because you also convolve around the temporal dimension. So maybe quickly, initially we were using TensorFlow, and our first prototype is in TensorFlow, but then we all switched to PyTorch, which I recommend because it basically cut down on development time, thus making the experiment faster. And so our initial model was so the starting point for our initial architecture was inspired by the paper from NVIDIA gesture recognition system from 2016. And there were some slight differences. So their data set was only about 1,500 videos. And they also used depth information from Kinect camera, whereas we used purely RGB images. And so the first network basically took a video, split it into n chunks, and fed each chunk separately into a 3D convolutional neural network. And the output for this chunk, the outputs for each of the chunks were averaged, and the average of the chunk prediction was a prediction for the entire video. And while this worked pretty well, we noticed that in order to model longer temporal relations, we needed to add a RNN layer on top. So now we would have the features from the CNN be fed into RNN, and again, the predictions of each column would be averaged. This also made our system real-time capable, because in this case, you can just make a prediction in the test time. You can just make a prediction for a single clip, and then save the hidden state and fed it over and over again, so that you're kind of imitating the training scenario in the test scenario. And with advances of deep learning, at some point we exchanged the 3D CNN columns for the SqueezeNet layers. It's basically a computational trick to get better features with less computational time. If you're more interested about reading SqueezeNet, I would recommend to go into the literature. This gave us some advances in accuracy and speed. But actually, for the final model, we kind of revisited the idea of splitting the video into chunks. So previously, the intuitive behind splitting the video into chunks was that we compute the part of the video, and then we kind of have some features that correspond to each time step of the video. We feed it into RNN so that we have like a timed sequence, and then we get the predictions. But for the final model, we decided to feed an entire video into a 3D convolutional neural network, with the convolutional filters being having stride 1 on the temporal dimension, and 3 respectively for the spatial dimensions. And what that brings us is, this gives us very good temporal features as well as the spatial features. And so in this case, this kind of n feature, so for the n frame video, you would have n feature vector, which then you would put into the RNN layer, and again average the predictions for each feature frame, or for each feature that that you get. So this is again how it may be a little bit more clear how it looks like. You have the video, you feed it into the 3D CNN network, then LSTM, then the softmax, and you see that the average would be probably most sensible. And so in order to demo the results, I'm going to show you a little clip. This is a video of the demo that is reduced to only 8 gestures. I will be, after presentations, around. If you wish to see a live version of the demo with 27 gestures, approach me and I'll show it to you. So in order to demo our system, we built a client service system using Python and JavaScript. It basically consists of several parallel processes. One is responsible for the inference, one is responsible for the video capture, and one is responsible for HTTP servering. And as I said, initially we were using TensorFlow. In TensorFlow, we save a network as a protocol buffer, and then we just load it into the memory and kind of session run the nodes that you're interested in. Right now, we're using PyTorch, and in PyTorch, it's a little bit more complicated because you need the checkpoints, so the weights of your network, as well as the network definition. But this might have changed with the new ONNX package released by the IBM, I think last week. And so this is the demo. You see a person performing different gestures just using a laptop camera. And it works, as I said, on 16 frames per second. And I think maybe that's enough. Oh. And so what you might also find interesting is that The demo runs on an embedded device from NVIDIA. It's an NVIDIA developer kit TK1, and it has a Kepler GPU with 4 GB of memory, built-in memory. So it's also embedded. And since the demo, we've been continuously working on collecting more data and building models that can understand more things. And we actually also published another data set, which we called the something something. And it's a data set of basic interactions with everyday objects. So our goal here is to build a system that can understand physical relations between objects. And it's called something something because you would find labels such as moving something towards something, and the workers would fill in the something something, so they would use everyday objects that they choose to. This data set has around 110,000 videos, and it contains, I think, 170 labels. And together with this data set, we've built a model that we call the super model. This is a model that can predict 300 different classes, also in real time. And this is the demo of it. So as you can see, this is the prediction that the network is most confident about. And this is it. Do you have any questions?
How difficult will it be to fill in something with particular objects?
So we're actually working on that right now. The problem is that, so there's, for example, 170 labels that are more or less uniformly distributed over the data set. It is not the case for the labels, because, for example, if you say pouring something into something, most of the workers, or maybe that's a bad example, but you can imagine that the workers try any object that they just have lying around closest to them while they're recording. So it's actually pretty difficult. We are thinking about combining the system with some kind of object recognition in order to make it easier for the network to also learn the objects. But it's actually a very good question. It's actually a very hard problem in this specific data set. I'm afraid I'm not. I can't disclose this information. I don't even really know.
Here was the question. In training such a difficult network, there's got to be a bunch of tricks that you use. So, were there any auxiliary losses that you use in, let's say inside of a deep CNN, or different backprop on maybe RNN layers and and the CNN layers? What are optimizer tricks that you use, stuff like that? Because it seems, really amazing. Congrats. I just like to know if there is anything that you can tell us about it.
It's a very good question, and so the process of training was super difficult at the beginning. So it didn't work for months, and we didn't use any optimization techniques, neither auxiliary tasks, but we spend a lot of time on figuring the right architecture. So, for example, we've learned that you need to normalize the outputs also before the RNN layer, as well as within the network. But from that point on, everything just started to work. And it is amazing how a simple network like that, the one that I showed you the last one, which basically is a 3D CNN network, you brute force feed a video into this network, followed by an RNN, and it works. And the reason, I think, for this is the data. So there hasn't been that much of optimization tricks as the huge amount of data that we just have and throw at it.
So pretty much just putting batch norm wherever I can, and putting data that is like new data, sort of like, you know, you don't really go epochs, but you just drop more and more data on him, and right,
Yeah.
so something like that.
Yeah.
So not really a lot of you know, really.
Well, I mean, depends how you look at it. Obviously, we spend months on finding the right
Oh, for sure,
architecture,
for
on
sure.
seeing what should go where, or how do I choose the frame rate for that. How do I sample my data? How do I, what input pipeline do I use for that? But the general answer for you, from me to you, would be not really auxiliary task as much as the right architecture combined with data.
All right. Thanks a lot. Thank you.
Yes.
But, and did you try some other compression techniques, like, I don't know, something based on wavelets?
No, we used JPEG compressions. I'm not sure if we tried wavenets. I'm pretty sure we just went with JPEG compression because I think it was proven to be the most efficient. Yes, I got that, but we didn't use wavelets.
Any other questions?
Did you try to use different architectures for recurrent neural networks than LSTM?
Yes, we also tried the simple RNN, but the LSTM worked better.
Okay, let's finish. Thank you very much for your presentations.